So hello, everybody. I'm very happy to be here and to have the opportunity to tell you about the detector development that we are doing within the baby Yaxo and Yaxo collaboration. So in order to tell you a bit in detail what we are doing, I will tell you about how we detect actions with helioscopes. I will tell you about the detail of Yaxo and baby Yaxo. What are the state of the art in this kind of experiments? What are the requirements and the strategy that we are going to adopt in order to reach the background levels that we need to attain? Then I will spend a little bit of time on our baseline technology, which is a gaseous detector technology that is called micromegas that we have been using in the CAST experiment. And I will show you the developments that we will do. I'll say a word about the alternative detector technologies that we are also doing some R&D, and these are the pictures that you were seeing in my first slides. So afterwards, I'll ask you to identify the detector technologies. And then I will say a very fast words on detection beyond solar actions, but Julia will tell you a little bit more in the seminar next week. So I don't think I need to go over this, but maybe from the point of view of an experimentalist, what I would like to say that it's very, very nice for us as experimentalists to be in an axion experiment that we have the relevant actional parameter space at reach in current and near future experiments. And to say also that experimental efforts in axion physics are growing fast, but they are still small compared to, for instance, WIMP experiment. So just to set a bit the picture. No. Yeah, so I will tell you about solar axion detectors, especially I will speak about CAST and what we are doing now for baby Yaxo and what we will do for Yaxo in the future. So for those that don't know about axion helioscopes, if axion exists, they are produced in the center of the sun. They will travel towards us, and if we want to detect them, we can put a big magnet that is pointing on the sun, and if we have the detectors that are able to detect photon conversions from axions, we can detect them when we are pointing the suns. Here you have the energy spectrum of Primakov conversions, and you can see that the energy range that we need to point is from, let's say, 0 to 10 keVs. And this is what we have done in the CAST experiment for 20 years, from 2002 to 2020. Here you see our magnet on a rotating platform that we orient towards the sun for about 3 hours per day. So just to say a word that we have not been the first helioscope that exists. So the current state of the art is CAST with a 10-meter long magnet, 9 Tesla magnet, but there was the Tokyo helioscope, and even before that, the Brookhaven helioscope that took data for a few hours. So we are the third experiment doing this kind of strategy. So CAST was, let's say, so it's the current state of the art, but what we want to do is Yaxo, that is conceived as a large-scale but realistic enhanced axion experiment. It will improve the signal-to-noise ratio by a factor of 10,000, and we are going to optimize all the ingredients of axion helioscope, that is, so the magnet, the optics, and the detectors, because here I didn't say, but in order to increase the signal-to-noise ratio, what we do is that we want to focalize the photons coming from axion conversions in a very small focal point in our detector. So like so like this, we can have all the axion signal in a very small signal here. So in YAXO, what we will do is to optimize each ingredient let's say, in order to improve the axion coupling constant. So here you see cast 10 meters long. Here you see YAXO, the conceptual design picture that we have. So as I said, we are going to build a large-scale magnet that will improve the magnet volume. It will have 8 conversion bores of 60 centimeters and it's 20 meters long. Here in CAS, it was 10 meters long and we had 2 bores. Here we will have, what you see here is 8 magnet bores with telescopes and with detection systems here, with X-ray telescopes and detectors. And we will track the sun for 50% of the time, while for CAST it was only 3 hours per day. So as you can see, it's a real optimized helioscope experiment. Sorry? So, in fact, here, what you see, you have, it's the conversion bore is where you have the magnetic field that you want. Yes. I hope I answered you. Yeah. So in fact, the conversion bores are in here, and in here you have the coupling of the conversion bores to the telescope and the detectors. So to show you a bit what kind of sensitivity we can achieve, here you have our usual coupling constant as a function of mass, and you can see so the sensitivity that we reach with CAST. You can see here what we want to do with YAXO. So you see that over all this large dynamic range of masses, we can improve by more than a factor of 10. But in order to build YAXO is quite ambitious. We thought that it was, in order to have a first stage, I am going to talk now about baby YAXO, which it's an intermediate experimental stage before YAXO. So instead of 8 bores, you have 2 bores of dimensions that are similar to the YAXO bores, with detection lines that are representative of final ones. The magnet will test the final design of the YAXO magnet, and then all the other systems, the tracking system, the detectors, the telescope, will test final YAXO magnet, and this is much easier to build a magnet like this that our big magnet for YAXO that is 20 meters long. So as you have seen from my previous plot here, baby YAXO will also reach relevant parameter space that has not been reached by our experiments. So now I will just say a few words about the different ingredients of baby YAXO before going to detectors. So here you see the baby YAXO magnet. So for helioscopes, we need a transverse magnetic field for converting axion into photon. As I have shown, the detector sensitivity is proportional to the length squared, diameter squared, and magnetic field squared. And the baby YAXO magnet that you see here is 10 meters long. Here is where you have the magnetic field, and with about 2 Tesla of transverse magnetic field over a free bore, with a volume of about 8 cubic meters. Here, maybe you have an idea a bit more of what is this magnet bore. So you have common coil superconducting dipoles with a coil length of 10 meters. So for 11 meters, so it produces a transverse magnetic field for 11 meters with a free diameter of 0.7 meters. And it will be operated with a temperature below 5 K. and it's based on niobium titanium superconducting coils. So the final design is being finalized now, and we hope to have the technical design review at the end of the year. So another ingredient of the helioscope, important ingredient, is the baby axo optics. So here you can see, so here you see where it will be placed before the detectors. So in baby axo, we will have two kind of optics. One is the custom approach that is being with inner part aluminum foil or segmented glass optics. Here you see the groups that are participating to this effort. The outer part will be done by INAF and DTU, and it's based on the technology that was put in place by the NuSTAR satellite experiment. The design of the support structure and vessel and calibration are on the way, and it's a collaborative effort between all optics institutions and MIT. And this kind of optics could be ready for test and fabrications in the next month. We have already existing telescope that was used for the XMM experiment. So it was a spare of the XMM flight, and the optics are currently in the Panther X-ray facility in Munich at DESI. So these spare optics seem to be in very good state, and they are suitable for baby axo. And already the pre-calibration took place in February a few months ago, and there is a kind of document for loan agreement between ESA and DEXI. So this telescope already exists. Okay, so with this introduction, I think now I can go to the detector development for baby axo. So here is what we are going to talk about. So we need a high detection efficiency in the region of interest that our actions will be in. So from 0 to 10 keV. In this region of interest, we need very low background. Very low background means 10 minus 7 counts per keV per centimeter square per second. So this probably doesn't tell you more. It's not very easy to understand what it is, but it means less than one event per 6 months of data taking. So this is really very ambitious. And in order to reach this kind of backgrounds, we need to use shielding. We need to use materials that are very radio poor, and we need to use advanced event discrimination strategies. So the baseline, yes? This number is after focusing. So I will tell you about this. The sensor that we are using now is 6 square centimeters, so it's quite big, but the spot is a few square millimeters. So we are using a bigger sensor that where your photons will be concentrated in. In fact, it's good to have a bigger sensor than. So, sorry. So the baseline technology is gaseous detectors that we have used in the CAST experiment, and I will show you what kind of performance we got. But as I was saying, we are also using some other technologies that I will say a few words afterwards, because they are complementary to these gaseous micromegas detectors. So here you see the detector that we have used in the CAST experiment. So it's a small TPC. It's with 6 square centimeters of very radio poor micromegas technology that is made of copper and kapton. We are using an argon-based mixture. We have a conversion gap here. You have 3 centimeters of gas, and the amplification gap in the micromegas is 5 microns. And in order to let the converted photons into our detector, we need a transparent X-ray window, which is 4 micron aluminized mylar. And we are using some readout electronics inherited from the T2K experiment. So here you see a picture of the implementation that was used in what we call the YAXO Pathfinder at the CAST experiment in 2014 and 2015, and also in later data taking periods from 2019 to 2021. And here you can see a picture. Probably you cannot identify very well the different ingredients, but here you have the telescope. Here you have our chamber with the electronics here. And this is a small scale version of the YAXO baseline detection lines. So what an event looks like, here you see an event done from calibration data, 6 keV photons. You can see that in the detector we have a quite concentrated signals in a small spot, in a small region. And here you see what cosmic ray, which is a typical background event for us, looks like. So you see that is a much more extended event. And using this topological facts of the difference between signal events and background events, we can have a very important reduction of this is what we have, the raw background level. And this is what we get after selection cuts using the topological properties of our signal. And you can see that we can reduce the background by a few orders of magnitude. So here you have a full picture of the micromegas background as a function of time, and you can see that we have done this in several steps because we needed to optimize the technology. So by understanding our background and improving the shielding of our detector and improving the micromegas technologies, you see that we have improved levels of 10 to the minus 6 counts per keV per centimeter square per second. And in an underground laboratory where you don't have, you have a reduction of cosmic muons, you can even have this level here, 10 to the minus 7 counts per keV per centimeter square per second. For those of you that don't know, CAST was at surface level. So this is the level here, and YAXO will also be at surface level. It would have been much convenient to be on the ground, but to put such a big experiment in an underground site with a moving platform, it was too complicated, but obviously it would have been much better. Yes. Sorry? Yes, yes. In CAST, we had, yeah, you cannot see them here. We had partial VTOS because we had to fit the VTOS in the space we had. But in YAXO, we are going to design completely 4 pi muon VTOS. Yeah, sorry, I didn't say. No, detection line, I mean, let's say a line that is COP beam line, not what you are talking about. Yeah, I'll say a word about this after. So detection line, it means just the beam line where the detector is coupled to. So I'll say a word about what kind of background contributions we have. So I think it's just here. So To do so, in order to improve our setup, we need to understand the background sources. So we have different results that we can compare. We have the experimental results, what we have done at surface with cast, that is 10 to the minus 6 counts per kV per centimeter square per second. So this is our starting point to go to the baby axo target level that we need to improve by a factor of 10. So this is where we are now, and we need to get below this value here. On the ground, without cosmics, we in the on-the-ground laboratory of Canfran in Spain, we can reach 10 to the minus 7 counts per kV per centimeter square per second. So this level is representative of the intrinsic limitation of our current design. And this tells us that this factor of 10 is probably dominated by cosmic related events. Also, there's been lots of simulation efforts in order to understand where these events come from. So saying that the main background of cast are cosmic induced events related to X-ray fluorescence. Here you see the copper line at 8 kVs and the aluminium K alpha line. So this tells us also that this shift result is compatible with simulations indicated that in the intrinsic background of our detector would be below 10 to the minus, so 5, 10 to the minus 8. So in order to reach this intrinsic background, our proposed strategy is to combine test at surface, test at underground, and simulation in order to demonstrate that we can achieve the baby axo target levels. So the test at surface are to demonstrate all the overall background strategies. Test at underground will tell us about the intrinsic radioactivity of our detector. And then the simulations will give us insight on individual components of the background to support experimental tests. So we have different setups in Zaragoza and in CEOA-Saclay, where we have implemented a 4-pi muon veto, like you see here. Well, you cannot see very well, but you have the detector with a LED shielding and a 4-pi muon veto. We have tests on the grounds to determine, as I said, the intrinsic and cosmic induced events, and then simulations where tell us that we might be limited by cosmic neutrons. So these hypotheses need to be confirmed by the setups that we call YAXO D0, that it was the detector that we have used in CAST, and a new YAXO D1 detector that is supposed to be improved. And we have implemented a cosmic neutron tagger that has been designed and is being implemented here with 3 layers of plastic scintillators. So this is to give you a bit the overall strategy. Let me now go into a bit more detail on the new detector that we have implemented. We have designed the YAXO D1 detector. So it resembles a lot to the gas detector that is shown here. It's made out of copper that is very radio pure. It's a small chamber with this transparent window here. The surface, the active surface is 6 times 6 centimeters squared. And here we have readout strips with a pitch of 500 microns that allow us to identify the position of the events quite precisely. In this design, we are working also on a new electronics because we want to have radio pure electronics in the cast setup. They were not radio pure. We want to have as low as possible energy threshold. We will have an evolution of the current chip that we had in CAS with auto trigger capabilities. And there is a new architecture in order to have front-end cards that are close to a detector that will be made of radio pure components. And the the other part of the electronics will be placed a little bit further from the detector. So here you see the radio poor part of the detector, quite close to the detector, and the backend card, it will be placed a bit further. So this design is finalized. The cards are in production, and we hope that by the end of the year, we will be able to test it. The shielding design has also been optimized. So here you have 20 centimeter LED shielding around our detector here. And then here you can see a nearly complete 4-pion muon Vitor. And just last week in Saclay, we received this new shielding that was manufactured with low activity LED. So the Cosmic Vito, we are considering two kinds of implementation, one with one layer of plastic, 5 centimeter plastic scintillators, that is here, you see here the LED shielding, and there's also studied to implement 2 or 3 layers of plastic scintillations in order to reduce the neutrons. So we have already some implementations of these detectors taking data in Saclay and in Zaragoza. We have one detector in the underground laboratory of Canfranc, and then this is the final implementation in Baby Axion. So in the University of Zaragoza, so we had this YAXO D0 detector taking data with 20 centimeters of LED with a multi-layer Veto system. As I said, 3 layers of scintillators. So we have 57 scintillators. We are using another mixture of gas, xenon, neon, and isobutane. This allows us to improve the conversion efficiency of axions into photons, and also to avoid internal contamination of argon, and also to reduce the background at 3 keV given by argon. So there's been 24 days of data taking, and here you can see the spectrum after doing the analysis using the micromegas signals and the Vitos and the background. So here in linear scale and in log scale, and the background that we have achieved is of the level of 9⁻⁻⁷ counts per keV per centimeter square per second, with an efficiency of 80% at 6 keV. What is I didn't show this, it's about 20%, 25%, the energy resolution. Yeah, I didn't, yeah. So we have set up in the underground laboratory of Canfranc in order to be in a muon-free or reduced muon-free environment. So we have set up what we call a detector platform for YAXO, because like this we will be able to test micromegas, but also all the other detector technologies. So here you see what the lab looks like, the gas panel. Here you see the shielding. We have a calibration system in order to calibrate our detector a few every day, or well, as long as we want, the micromegas, and here the DAC computer. And this setup has been taking data at the beginning of the year for about 22 days of data. Here you can see the detector here at the back with the copper tube and the LED shielding here. And we had at the beginning some noise issues that have been addressed, but we have achieved. So here you see the background spectrum level of 6 × 10⁻⁷ counts per keV per centimeter square per second. So this is a bit higher of what we were expecting. But we are using a new gas, so we have to understand if it comes from this in a closed loop using some filters. So we might be suspecting that we might have radon contamination from the gas filters. We are using a bit of different shielding geometry. So this could come also from this. And maybe the detector performance was not optimal. So at the moment, we have replaced the current micromegas detector that was installed here by a new one with an improved signal to noise ratio. So we hope that in the next months, we will be able to understand this discrepancy. We were hoping to have levels below 10 to the -7. Okay, so now this was for the baseline detector technology, but as I said, we have other technologies in mind because they are complementary to micromegas. Micromegas is a gaseous detector with energy resolution of about 20–25%. Other technologies, they are much better energy resolve, so they are complementary. They have better also energy threshold, and they can also be made of very ultra pure materials. So these features allow for the investigation of fine structure in the axion spectrum. So micromegas can be a kind of discovery detector, and these are energy. Once you have discovered the axion, probably is nice to have this kind of technology. If a positive signal with low threshold and good energy resolution, possibly you can determine the mass of the axion and the coupling of the axions to electrons. Also, having different technologies, you can minimize the systematic effects and reinforce claim significance. So we are studying this kind of technology. So another gaseous detector technology that is called grid peaks, bolometers, MMC, and transitional sensors, and a silicon drift detectors. And at the moment, these technologies, they need to demonstrate that they can achieve background levels of the order of what is needed for baby axion, because they have not up to now done the optimization for baby axion implementation. So at the moment, they are designing and they are optimizing the materials of construction, and they are doing background studies with different shielding configurations. So this is what I'm going to show in the next slides. So let's go first here with the grid peaks detector. You see that the geometry looks very much alike of the cast micromegas detector. It's a gaseous technology. It combines a pixelized readout with an integrated chip that you can see here at the bottom. It's able to measure very low energy X-rays of the order of 200 electron volts. It has an ultra-thin window that allows for very good transmission of X-rays, and it has also been used in cast, so it has also gone off phases of optimization. So it uses the Timepeaks tree that you cannot see here, and the grid, the micromegas grid, is made by photolithography on top of this ASIC. The holes of the micromegas mesh are aligned with the chip, and you have an amplification gap by these small pillars of 50 microns. Single electrons are measurable, and you use the time of arrival and the time of threshold information for signal discrimination. So they have a new optimized detector that you can see here. You see all the ingredients, the entrance window, the grid peak chip, the field gauge. And the next step towards baby axion is to use all these with radio pure materials to do background characterization and to understand the energy response. And for the moment, they have a prototype with only one chip, but they are going to surround this one chip, which is 1 centimeter squared by these 6 outer chips as Vito for muon tracks. So let's go to the other technology, silicon drift detectors. So they are detectors with a small readout electrode with low capacitance, with very good energy resolution, 200 electron volts at 6 keV, with also very low energy threshold. They don't have entrance windows, so this is an advantage because they have a very nice threshold. And here you can see the efficiency as a function of energy, and you see that they have an efficiency over the whole range of the axion spectrum, very close to 100%. They can make the detector of semiconductor grade materials, so there's great potential for low background operations. They have implemented this detector in the Tristan experiment, and for YAXO, they have built an optimized detector that they call TAXO. And here you can see what it looks like. It has a passive, so here you have the SDD with a passive shielding setup with a compact LED castle. And the aim of this is to demonstrate that they can reach 10 to the minus 7 counts per keV per centimeter squared per second. And the current background with a demonstrator that they have already is of the order of 10 to the minus 6 and is limited by some polyimide material that they have used, but they have in view of using an upgrade silicon interposer that should allow to diminish this background. So they have a detector at LSC in Canfranc, and they have a prototype at TUM in Germany. So they have the 2 background measurements on the ground and at the surface. So here you see a bit the strategy. This is where they are now with the TAXO demonstrator. In the next months, they will improve the passive shielding and the materials of the detector. And then next year, they will have an active muon shielding in order to reach the levels below, hopefully, let's say, first 10 to the minus 7 and then 10 to the minus 8. So another technology is the metallic magnetic calorimeter. These are cryogenic microcalorimeters operated at very low temperatures. They are based on the parametric temperature sensors, and they can reach really very good energy resolutions that you see here at 6 keV of 1.5 electron volts. They have very high linearity, and they have a large bandwidth with very low threshold. They have made already data taking at ground and without any Vitos. So they have reached levels of 10 to the minus 4, but at the moment they are developing a cryogenic MMMC-based muon detector in order to reduce these events. And they will design a cryostat to be used with a room temperature muon-weighted or scintillating panel. So this work is ongoing. So the last technology is the transition edge sensor technology. These are also cryogenic sensors that use the temperature-dependent resistance of the superconducting phase transition. They have in imaging geometry where they have the X-ray detector here with silicon or germanium wafers mounting between the two vectors in order to reduce muon events. And here you can see the 200 germanium vector with a 4mm hole that you can see here. And here the 2-inch germanium wafer with 3 TS. So these are being characterized in the laboratory. So now a few slides about some details of baby axion going beyond solar axions. So all the technologies I have shown up to now, it was for solar actor conversions, but baby axion might constitute an infrastructure where you could look for other kind of actions. So actions coming from supernova, other non-Primakov solar axion production, or optimizing detectors for precision physics, or even becoming a haloscope if you use microwave cavities inside the magnet. So if you are able to detect both spectrum, the ABC spectrum and the Primakov axion spectrum, you might be able to distinguish among different axion models. If you measure the spectral shape, you can also maybe give some indication of the axion mass. And then if you detect the 14 keV peak from the 57 iron transitions, you can have some sensitivities on the coupling constant of axion into the nucleus. So for instance, if you have sufficiently close supernova that explodes, you could detect actions from this supernova with energies of the order of 100 mega electron volts. But this would require that you have a gamma ray detector here on the other side of the X-ray detector technology. So this might be of interest to be studied. And it's complementary, and it's possible to implement this kind of detector in baby axion. So these are things that we need to look in the future. Also, in CAST, there has also been some R&D in order to use microwave cavities in order to convert our helioscope into a haloscope. And there has been some R&D in order to develop new geometry concepts to scale in volume, but keeping high resonance frequency. There has already been a publication where there is this kind of limit, and this will probably go on in JAXO. And here there's some studies where probably there will be a publication very soon, and where there is very competitive prospects for actions of 1 to 2 microelectron volts using 4 times 5 meter long cavities with tuning slab, low noise, and Bohr's cool down to 4 to 5 Kelvin. So with 2-year data taking. So I think I come to the end of my talk. So I hope I have convinced you that in JAXO we have a very unique physics case where discovery is possible, even already at our baby JAXO stage. We hope to commission our experiment in 2028. We have a very active detector development with a clear roadmap for the detectors of baby JAXO. We have 2 types of detectors, discovery and energy resolution detectors. Micromegas detectors are the baseline for baby JAXO, but we have other technology that have very fine performance on energy resolution and threshold that could be interesting for all the physics case of baby JAXO. So thanks a lot. I but not knowing where to look for, it's probably, yeah. Yeah, you would not know that they come from. What is your question? Sorry. Yes, I think you can infer the mass if. Yeah, I think. Yeah. Yes, I forgot to say thanks to all the people that contributed to this talk. So I think there is a plot. Yeah, here this I think is the number of events 10, 100,000, 10,000. Yeah, with a certain, yeah. Yes, yes, I didn't speak about this, but in order to get sensitivity to higher masses, here a bit like we did in CAST, in order to reach this kind of sensitivities, you are going to put a buffer gas, helium-4. Yeah, so this is expected after a few 2 years of data taking. Probably you will put a buffer gas inside the magnet. So I think yes, but as it has not been implemented, we have to look. But I think they are confident. So it's I don't know, it's 10 hertz per, yes, yeah, a few hertz. So normally it should be okay, but yeah, they have not implemented their, yes. There's dark photons as well. I mean, I'm not the best to answer to this question, but yes. So there's dark photons. I don't know if you will speak of other things, Julia. Yes. why we use this kind of design for baby axion. Eight. Ah. Mm. So with the microvolk detectors, so microvolk is just a micromegas made of copper mesh. It's a special micromegas. With argon isobutane, we are probably at the level of the best energy resolution we can get. With argon, xenon, neon-based mixture, the resolution is a bit degraded. But yes, for this kind of detectors, I would say with this technology, with the previous detectors that we made, we are quite at what we can expect of best we can do. But we have seen that, in fact, what counts for us is the background rejection. So, in fact, if you have an event, but you can kind of determine whether it's background or not, is not the main. It's what you can do with the topology of the event, at least with the micromegas background that we have. For other technologies, maybe it will be a bit different. Yeah, the energy is from the clusters in the yes. Yeah, I'm sorry, I had the plot of the cluster energy, but I didn't include it here. So yes, it's just to. So just to play this little game. So this is, but in fact is not fair because I didn't show exactly the same pictures, but this is SDD, this is transition edge sensors, this is micromegas, but I didn't show this plot. So it's just here you can see the micromegas mesh. This is MMMC, this is another TS, and this is grid peaks. So anyway, now you are an expert on identifying detector technologies. But they all look, I like it because they are all made of copper, this nice material. So yeah.